Well, welcome back to Geography 212. I'm going to show you the highlights of Chapter 4 regarding heat and temperature. So first of all, what's the connection, between temperature and kinetic energy? Well, you know that all matter is composed of molecules, particles that are continually vibrating, continually in motion, all right? And the energy represented by this motion is called kinetic energy. Temperature, as you can see, is going to be directly proportional to the average kinetic energy of these atoms or molecules. In other words, directly proportional to how much they're moving. So another way to look at this is that the higher the temperature, the more movement you're going to get in these molecules, and the lower the temperature, the less movement you're going to get, till you get down ultimately to absolute zero, where there is the cessation of all movement. So no movement once we get to absolute zero. So speaking of absolute zero, you can see here across this slide, there's different ways we measure the temperature. Okay, there's the Kelvin scale, which some call the absolute zero scale. The Kelvin scale, as you can see on the far left there, is zero is as cold as it can get. That's absolute zero. So there are no negative temperatures in the Kelvin scale. And then you can see, for example, on the Kelvin scale, 273.15 degrees is freezing. Okay. Now, if we slip over to the Celsius scale, 0 degrees is freezing. So in other words, that's where the zero is going to be there. So anything above zero is thawed out. Anything below zero is frozen on the Celsius scale. Then we have the Fahrenheit scale, which is really kind of an oddball, and very, very few countries on the planet are using Fahrenheit anymore. Most countries have gone totally metric, and Celsius is part of the metric system. As a matter of fact, there's only 3 countries in the world that I'm aware of that don't use Celsius, and be the United States, Myanmar, and Liberia. So it's kind of odd the United States hasn't gone to the Celsius scale, although we're seeing more and more of that come in. So there are the 3 scales. Anyway, let's move on here to the next slide. How do we measure thermometer? And this is what we would call the instrumental record. I've referred to this before, refer to it again. The instrumental record is simply measuring things with instruments. So in terms of temperature, we have different types of thermometers. Okay, most of you are probably familiar with what we call a liquid in glass thermometer. You can use any liquid you want inside a thermometer like this. Now what they are, it's an evacuated glass tube with liquid in it. Liquid responds to temperature changes by either expanding when it gets warmer or contracting when it gets cooler. So you can use any liquid you want. Now, I've put this in here that primarily we're using mercury or dyed alcohol. You've probably seen colors of red and blue and that kind of thing. And that's alcohol with just some dye put in it. Now, I've put in here, I moved down from British Columbia 4 years ago, and almost every thermometer in Canada uses alcohol. Now I say why, I don't know if anybody's aware of this or not, but alcohol will not freeze until it's about minus 190 degrees Celsius. So mercury, however, will freeze around minus 39. And the problem with that is that, we get a lot of temperatures colder than 39 below Celsius in Canada. So mercury would freeze in thermometers in cold climates, and so that's why alcohol is the preferred liquid there. You can see there's other types of thermometers. Probably a good idea to take a look at the pictures of them in your book. A lot of thermometers today at automated weather stations are electrical resistance thermometers, and so they're becoming more and more popular today. In terms of measuring temperature, and when we talk about official temperatures here, there are pretty strict protocols around the world for measuring temperatures if you want it to be recognized as an official temperature. First of all, you can see that photograph on the right. The sensors, whatever sensors we're going to be using, have to be shielded. And you can see they're white. That's going to, remember, albedo. A white surface will reflect most of the shortwave solar radiation. So you're not heating that the little screen thing up because of shortwave solar radiation. You don't want to measure shortwave solar radiation temperature when you're measuring temperature. You want to measure air temperature. So it's in the shade, generally have free flowing air, and you can see that you have that in there. Okay. Another issue in terms of protocols for measuring temperature, it needs to be only about 1.5 meters above the ground. And the ground needs to be a natural surface, all right? In other words, it can't be dark asphalt. That's going to absorb a lot of short wave and heat up and then throw a lot of long wave up. So we're pretty particular about what we will accept as an official temperature around the world. So I put in here, now actually look at the photograph on the right there. You see that white louvered box where there are instruments, including thermometers in there. That's called a Stevenson screen. You can see it's white, so it reflects shortwave solar radiation. And you see the louvers in it that allows the free movement of air in there. That happens to be the station at Furnace Creek in Death Valley, California. Now, Death Valley, California, as you can see here, has the highest recorded official temperature in the world, 134 degrees Fahrenheit. Now, it's only recent, really, that this has become recognized as the official highest temperature ever recorded, even though it was back in 1913. Up until a few years ago, there was a temperature record of 136 degrees at a station in Libya in Africa. And there was had been suspicion that that was an inaccurate measurement. And suffice it to say that the World Meteorological Organization sent over some people to have a look at this and do some research into this. Anyway, they decided that it was an inaccurate temperature, so they threw it out. So Death Valley, if you go into a lot of literature, you'll probably see Death Valley still listed as the second highest temperature ever recorded at 134. But I can tell you that within the last couple of years, it's by default become the highest temperature because we've thrown out the 136 degree reading in Libya. There's some interesting data there about some of the temperatures in Death Valley. If you've never been there, it's a wonderful place to go. I've spent a lot of time in Death Valley. Just a beautiful place, as long as you don't go in the summer. But you can see it's had some pretty good temperature records there. Later on, we'll get more into the causes. I've just listed a few of them there for you as well. But we'll revisit that later on when we talk about the global circulation model. All right, in terms of lowest temperatures ever recorded, it turns out that the lowest temperature ever recorded is at a Russian station in the Antarctic, at the Vostok station, back in 1983. You can see that in Fahrenheit, 128.6 below zero, which translates to minus 89.2 Celsius. So that's the coldest ever recorded. I thought you might be interested in the coldest temperature ever recorded in North America. And it happens to be a place called Snag, Yukon, back in 1947 at minus 81.4 Fahrenheit, which is equivalent to minus 63 degrees Celsius. Where is Snag? Well, if you can visualize the border between Yukon and Alaska, about halfway from north to south, Snag is just barely in the Yukon. This is also very close to being in the interior of Alaska. So in terms of heat transfer, this is an important concept in meteorology. In terms of temperature gradient, what is temperature gradient? Simply the change in temperature over distance. Now, for example, and I'll show you a graphic of this in a few minutes, as you might suspect, surface temperatures are much higher in the equator than they are at the poles. So in response to this, we get heat flowing from equatorial regions toward the poles. And again, important concept in both climate and meteorology. So how does heat flow? Transfers and things like that. Well, heat flows through a vacuum via radiation. We've talked about shortwave and long-wave radiation. From the sun to Earth, for example, that shortwave radiation is traveling through a vacuum. Conduction is simply heat transfer through a solid. And convection is heat transfer through a liquid. Through a fluid. Keep in mind that the atmosphere is a fluid. Fluid isn't just water, okay? So when we talk about movement through the atmosphere, we're talking about movement through a fluid. It's very complex. All right. Latent heat, something I'm going to point out here in a minute. This is a phase change in H2O. And the point is, actually, I think I'll move on to the next slide. Actually, let me go to this one here and I'll go back. Latent heating. Here, if you start from the left, you see a snowflake. It's indicating a solid. And then if you go to the right, you see what we call vapor or a gas. All right. So if we move from, say, left to right, in other words, if we follow ice through into liquid water, through into vapor, it's going to require a great deal of heat as it moves from left to right. If you look at this top line here, you'll see latent heat absorbed from the atmosphere. So in other words, obviously, it requires heat to melt snow into water, and then it requires a great deal of heat to evaporate liquid water into water vapor, which is a gas. However, when we go the other way, when we take water vapor, H2O gas, and then we condense it to a liquid, a great deal of heat is given off. There's your latent heat, okay? And then when we go from a liquid H2O to solid H2O as an ice, we give up even more heat. So heat is released to the environment. Now here's an important concept in meteorology then. So when we see clouds developing, please keep in mind, clouds are not water vapor. They are not gas. They are liquid or ice, okay? Typically here in the summertime, our clouds are going to be liquid in the southwest. So when we get water vapor, okay, evaporating, and we get it condensing then into clouds, a great deal of heat is given off. That's called latent heat. So a lot of times during this monsoon season, we start getting clouds developing, we get water vapor condensing into liquid cloud droplets, heat's given off, and that further drives the development of the cloud. So latent heating is a very important concept in meteorology. I go back to this slide. Convection is a very important heat transfer process in meteorology, and I'm suggesting here it's the most important process. In other words, how is heat transferred through the fluid of the atmosphere? And a very simple diagram here. You can see that typically as the ground heats up, it's going to heat the air above it. This warm air rises. As it rises, it gets further and further away from Earth's surface, so it cools, condenses. Remember, that's liquid water. That cloud there is liquid water, tiny little cloud droplets that stay buoyant in the atmosphere. But as that air cools off, it gets denser and it's heavier, and then it can flow back down to Earth's surface. So this is something that's called the convection cycle. Okay, another concept, a very important one, is called specific heat. Really, a way to think about this is how much heat can something hold, okay? If you take a look at the chart over there, what you find, water at the top. Water can hold a great deal of heat. So think about this. Our oceans hold a tremendous amount of heat, okay? So there you go. You can go on down the list there, and you can see that, you're ending up at gold, doesn't hold a lot of heat, so it's going to lose its heat very quickly, that kind of thing. So this notion of thermal inertia, it's a fairly simple one, really. It's a resistance to a change in temperature. And what I'm saying here is that large bodies of water really show a great resistance to temperature change because they hold so much heat. A little bit of input of heat or cold isn't going to change the temperature of an ocean or a large lake very much. So what I'm getting at here is that any cities or weather stations that are close to or downwind of an ocean, and now in North America we're talking about the west coast of the United States, the west coast of Canada, California, Oregon, Washington, British Columbia, and Alaska. Those areas along the coast there are immediately downwind of an ocean. They don't experience much average annual temperature change. We call those maritime climates, okay? So one of the examples there, if you look at the graphic, the blue line on the graph is San Francisco. So between January and December, there isn't a great deal of temperature change because San Francisco's sitting right there downwind of this huge body of water, the Pacific Ocean, and its temperature simply ain't going to change very much. However, you get inland away from these areas of thermal inertia, like large bodies of water, you're going to see a much bigger temperature change. between winter and summer. We call these continental climates, and the example given in the graphic there is St. Louis, which sits pretty much in the middle of the United States. So thermal inertia then, the closer you are to a large body of water, particularly if you're downwind of it, you're not going to show a lot of variation in temperature. Now, a lot of people will look at the East Coast and go, well, hey, isn't it the same there? No, it is not, because if you think about the East Coast of the United States, it is downwind of the interior of our continent, which is a continental climate. So generally, wind moves and weather systems move from west to east at our latitude. So places like Philadelphia, New York, Washington, Boston, they really are a continental climate and do experience wide changes in temperatures throughout the winter because most of their weather is coming off the interior of our continent. This is showing the global heat imbalance, meaning that in the equatorial regions, we're getting a surplus, as it were, of land being heated up by shortwave solar radiation. And then once we get north and south of about 32 degrees latitude, we see a deficit. In other words, you're getting, not getting very much solar radiation. But our planet's climate tries to balance that out. We get a lot of heat transferred from the equatorial regions toward the poles. And we get them, you can see down the bottom there, poleward heat transport. In other words, how is heat transported from equatorial regions toward the poles? Well, one, air masses. Warm air masses can move from equatorial regions toward the poles. Storms, particularly tropical cyclones, which what we call hurricanes here in North America, they transfer a tremendous amount of warm heat and energy from the tropical areas. Okay, they're very important tropical cyclones. Ocean currents, very important as well. And we'll take a look at some of those. There's a very important one along the east coast of the United States called the Gulf Stream current. All right, heat transport again. The first one I'm talking about here is air mass exchange. We've already talked about air mass properties. Remember, it depends on where they come from. So in other words, if an air mass is sitting over a cold ocean, it's going to have the properties of being cold and it's going to be fairly moist. Okay, heat transport by storms, I just mentioned it earlier, but tropical storms, tropical cyclones like hurricanes contribute greatly to this poleward movement of warm air. Now, ocean currents. If you take a look at the graphic to the right, you notice that's the southeast coast of the United States, Florida Peninsula sticking out there. This is color-coded to temperature. So look at the surface temperature of the ocean water in there. The red and orange is very warm, yellow is very warm. This is the Gulf Stream current that flows from the Caribbean up the east coast of the United States and actually carries on into Europe, places like Ireland, Great Britain, Scandinavian countries. And this particular ocean current gives that area, Europe, Scandinavia, very much warmer winters than they would have if they didn't have the influence of this current. Okay, let's just take a look at variation of air temperature, movement of air. Okay, air mass advection. You can see those two arrows over there, A and B. All that term advection means is the horizontal movement of air. They've heard the term convection. That's the vertical movement of air. Advection, horizontal movement of air. So a pretty simple concept here is A and B. A is depicting something we call cold air advection. And it's a movement of colder air into warmer area. Generally, there'd be a cold front out in front of that. B is simply warm air advection, horizontal movement of warmer air into colder air. And in this case, you generally would have a warm front out in front of that. Okay? So this air mass advection, we can also, let's take A for example. As that cold air continues to move south into the United States, it's going to modify. It's going to get warmer. So these air masses will change over time, again, depending on the surface over which they lay. And concomitantly, the air mass B, that's indicated by B there, as this warmer air flows from south to north in the United States, it's going to gradually modify into colder air. All right, another variation of temperature, an important concept, is called the urban heat island effect. What is it? Well, basically, it's the core of a city being warmer than the outlying areas. And why is it warmer? Well, number one, relative lack of moisture. And why is that? If you think about it, in urban areas, we have a lot of parking lots, we have a lot of asphalt surfaces. These are what we call hardened surfaces. When it rains on a surface like that, it evaporates very quickly. Just take a look at it next time it rains in your neighborhood. Notice how the roadway will dry out long before the grass or the vegetation along the side. Now, what's the importance of that? When a surface is wet, incoming shortwave solar radiation will work to evaporate that water before it warms the surface. So that surface isn't going to warm until all the liquid water has evaporated off it. Hardened surfaces evaporate the water much more quickly than vegetated surfaces. So once that surface is dry and all the water's evaporated off, it starts heating up. But vegetated areas are much slower to dry out, therefore they're much slower to heat up. So by replacing original vegetation by hardened surfaces, we are making them drier, therefore they're going to heat up more quickly. Okay, so a lot of these, take a look at a black asphalt surface. We're going down to the second bullet, that absorbed heat raises temperature. Black surfaces are going to absorb a lot of shortwave solar radiation, okay? So they're going to heat up. Greater concentration of heat sources. You know, cars, their engines get hot. We're running around. That heat flows out into the environment, okay? Air conditioners, furnaces, things like that. Multiple reflections, okay? Think about tall skyscrapers and shortwave solar radiation coming down and just zigzagging down and bouncing off all the sides. That's going to actually trap radiation. Sometimes we refer to these as radiation canyons created by these tall skyscraper buildings, okay? And just building materials are going to conduct heat more easily than soil and vegetation. There's a whole lot of reasons, and those are the main ones, why city cores, large city cores, have higher air temperatures than the surrounding areas. All right, that concludes chapter 4.